Okay, depressed cubics. So this is a whirlwind. Just how do we solve that? All right, so that's called a depressed cubic. It's got no quadratic term. I'm going to rewrite it in this form, put the constant on the right-hand side, because that's what the 16th century Italians did, because they couldn't write something like that because they didn't acknowledge negative numbers, right? So if they had it like that, then that would mean that that would need to be a negative number, and they didn't like negative numbers. Quite ironic, considering they... What's that?
If they don't like negative numbers, should you write 5y minus y cubed equals 2?
They didn't mind subtraction.
Yeah, but they're saying equals minus 2. They don't like negative.
Oh, yeah, so they wouldn't have done this one. Yeah, but this is my example, and yeah. Okay, so there's no reason to present it in this form other than that it ties in with history. And I'm using y for the depressed cubic and x for the general cubic so that we can sort of keep track of what equation we're doing. All right? So rather than go through and solve this numerically, because it's a lot more complicated, we're going to solve it algebraically. All right? But the details will be a bit later. There's the solution. All right? We'll see how we got there, but that's the solution. So if that's your depressed cubic equation, then that is your solution. So it involves cube roots, nested square roots. This discriminant symbol is that, and the b and a come from your equation, okay? So there are similarities there with quadratics. This is a discriminant. It does distinguish, like how many real roots the cubic equation will have. Every cubic equation will have one real root, guaranteed, and then the other two will either be real or complex. All right, so to apply that here, we're doing that form, that equation, expanding this out. There's our values for a and b. Just note that half b is -1 because we want half b here. Is our expanding for delta. We get -98 over 27. Told you I made it so it would have nice numbers. And there is what the solution tells us, okay? Just going to press the next button without comment, okay? How many real solutions did this particular cubic have? 3.
3.
Yep, it went like
All
that
real
across
solutions.
the... Right, 3 real solutions. What's this doing there? If you're an experienced 4-unit maths teacher, then you would probably recognise the solution to this problem reasonably quickly. I'm not an experienced 4-unit maths teacher, so I've worked it out in considerable detail. All right. So 3 real solutions, an expression involving complex numbers. What's going on? Well, it simplifies to this. You know, to five significant figures. So 1 plus that I plus 1 minus that I gives us 2. Okay, so the solution, I should say a solution, is y equals 2. We saw that this has 3 real solutions. This is giving us one of them. So you can find the others by factorising and that sort of thing. You know, polynomial division. Or this involves taking cube roots. Who says the cube root of that is that? Right? This has 3 cube roots, doesn't it? Right? So we've taken the, you know, the principal cube root or the most obvious cube root or whatever, but there are other cube roots, and I believe, but don't quote me, that if you take, you know, various complex cube roots of those and combine them in different ways, you'll get the 3 solutions. That makes sense, right? Okay, so back to our original one in X, a general cubic. We made that substitution and arrived at that depressed cubic. We solved that and found it had y equals 2. So now we reverse substitute, right? X equals y plus 2, so it's 2 plus 2 equals 4. And so it's just shifting it back, isn't it? All right? So this has x equals 4 as a solution. All right? There it is. I believe that this method always gives us the rightmost real solution. I don't know if that's actually true. It wouldn't surprise me if perhaps if the leading term was negative, then it would give you the leftmost, for instance. But I haven't spent much time thinking about it. So here's a quick summary so far. To solve the general cubic, you can make this substitution, and then, well, sorry, it's not so much make this substitution, that's the machinery behind this, right? So to solve it, x does equal this, where bang, 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 bang. And to work it out, you go in reverse, right? You have to work those out because you've got your A, B, and C. Then you can work out your delta because you've got your capital A and capital B. Then you can work out your Y because you've got your B and your delta. Then you can work out your X, as demonstrated here. Well, soon. So, this comes from the substitution that we made. This comes from solving the depressed cubic, which we're going to look at in detail. Oh. And just a comment here, we're doing this part algebraically. The part we just did with the substitution, of course you can do the substitution of x equals y minus a third a and do all the expanding and simplifying in terms of a, b and c, right? Quite hairy, but not difficult, it's just algebra, right? So I'm not doing that in the presentation. It's in the article. Quick example, to solve this one, all right, if we work out our a and our b, then we work out our discriminant, then we work out our y, then we work out our x. Okay, so I wrote a computer program to do all this, because that's what helped me to find an equation with nicer solutions.